All right, this is the last section that we are going to deal with for trig this year. We are looking at some unit circle basics and the graphs of sine, cosine, and we'll try to get to a little bit of tangent graphs as well. This first page just has a blank template for the unit circle that you could use to practice recreating it. So a unit circle is a circle that has a radius of 1 unit. For every angle, there is a point where the terminal side of the angle intersects the circle. The coordinates of these points are cosine theta and sine theta. In other words, x would be your cosine value and y would be your sine value. So if you think of a 30, 60, 90 triangle, we've talked about dividing the top half of our circle into sixths or 30-degree increments. So we have 30 degrees or pi over 6. If we picture that triangle, we have a 30-degree angle here. We have an opposite side that is 1/2. Our y-coordinate is 1/2, and our base is the square root of 3 over 2. Radius here is 1. So when we look at our coordinates, we said our y-coordinate is the sine of 30 degrees, and our x-coordinate is the cosine of 30 degrees. So the whole unit circle is created that way, where we put our x-coordinate being the cosine of the angle, and our y-coordinate being the sine of the angle. If you think back to when we looked at our 45, 45, 90 triangles, we said our opposite and adjacent sides, we've got the square root of 2 over 2 for both. So cosine and sine end up being root 2 over 2. The nice thing about the unit circle is that we can look at filling in the first quadrant and then reflecting it to get the other 3 quadrants. So if I take this same point here, my 30 degree, if I reflect it over the over the y-axis, it lands over here. Notice that my coordinates are almost identical except my x-coordinate has flipped to be negative since I've reflected over the y-axis. If I take that point now and I reflect it over the x-axis, it lands down here. What changes when I reflect over the x-axis is my y-coordinate went from positive to negative. And then I can reflect it over the y-axis again and have it land here. My x-coordinate then would become positive again. My y-coordinate would still be negative. So all 4 of those dots that I've kind of enlarged have the same basic coordinates. You just have to think about what sign it is in each quadrant. And that's true for all of these points. I can take this point, reflect it over to here. I can reflect it down to here, and I can reflect it back over to here. And then I just look at how my x and y coordinates change sign. You'll get into a lot more about the unit circle next year in pre-calc. It says use the unit circle to verify the following. The domain for theta is all real values. In other words, we can continue to spin around that unit circle as many times as we want. It just makes our angle get larger. If we spin in a clockwise direction, we would get a larger negative angle. The range for y equaling the cosine of theta or y equaling the sine of theta. Either way, our range goes from -1 to 1. And if we look back at our picture here, our 4 main points, we are the farthest away from the origin at those 4 points. And in each case, our x value is going from -1 to +1. Our y value is going from -1 to +1. So if we want our x or our cosine values, our cosine ranges from -1 to 1. Our sine or y values range from -1 to 1. Going from 0 to 2 pi completes 1 full cycle or 1 full circle. Now, we are going to start looking at the graphs of y equals cosine theta and y equals sine theta. We can find those graphs by plotting all of the points where our first coordinate is the angle and our second coordinate is either x if we're doing cosine and y if we're doing sine. All right, let's look at a little picture here. When we start looking at a cosine and sine curve, this one here happens to be a sine curve. And if we take our values and notice as we go around the circle, okay, so as this point keeps moving around the circle, it is creating this curve. Okay, that is a typical sine curve. And again, our y-coordinates come right from those sine values, or our y-coordinates on our unit circle. Another way we can see a sine curve is with a spring. If we look at the spring moving up and down, its path would create a sine curve. All right. For our basic sine and cosine functions, when we haven't done any kind of transformations to them, we call it a period, or one full circle, and for sine and cosine, a period is 2 pi. All right, one full circle around would create a full chunk of our sine and cosine curves. Now, sine and cosine curves are like waves. They just continue in that same pattern. Our typical sine curve starts at 0 because when we look at our unit circle at 0 degrees, our sine value here, our y-coordinate is 0. When we are at pi over 2 or 90 degrees, our sine value is 1. So we're up here at 1. At pi, our sine value is 0. I'm going to pause the recording here and redo my board. All right. So we said at pi, my sine value is 0. So at 1 pi, I'm at 0 for my y height on my graph. Down here at 3 pi over 2, my sine value is -1. So at 3 pi over 2 for x, I'm down here at -1. And then by the time I get back to 2 pi, I should be back to a y-coordinate of 0. That is a typical sine curve. So it starts at 0, goes up to 1, back to 0, down to -1, and back to 0. That is considered one period from there to here. Okay? With a cosine curve, we are using our x-coordinates. So we are starting at a 1, going to 0, to -1, to 0, and then back to 1. So I'm starting here at a height of 1, height of 0, height of -1, back to a height of 0, and up to a height of 1. This is considered one period, or one cycle. So again, from 0 up to 2 pi, this is one period for cosine. Our tangent curve is a little different. The period for tangent is only 1 pi. And that period is kind of split. Again, we can take our x and y coordinates from our unit circle and we divide them. Y divided by x is tangent. So take our points on our unit circle. At 0 degrees, or 0 radians, if we take our y-coordinate divided by our x-coordinate, 0 divided by 1 is 0. So a typical one period for a tangent graph looks like this. And then that just keeps repeating over and over and over, that same shape. When we talk about even and odd functions, that refers to the symmetry. A sine curve is an odd function because it's symmetric to the origin. If you take that sine curve and you spin it around the origin, it's going to land back on itself, spin it 180 degrees. Tangent is also an odd function because it is symmetric to the origin. Again, if we spin our tangent curve, this piece here would land up here. Okay? Cosine, though, is a little different. Cosine is symmetric to the y-axis. If we take this chunk and this chunk of it, you can see that it is symmetric. So a cosine curve is going to be an even function because it's symmetric to the y-axis. All right, we've been talking about transformations of functions all year. You're going to see those same kinds of things show up with our tangent and sine and cosine, our trig functions. Our a value here Again, my board is off a little bit. Our A value is going to be our amplitude. That tells us if we've got a vertical stretch, a compression, or a flip. Now, amplitude, we said, is an absolute value of that, so it doesn't use the negative sign. The negative sign would just be telling me that my curve is going to reflect over the x-axis. And that is the same for cosine as well. All right, so we are trying to determine the amplitude of y equals 2 sine x, and then we're going to graph a basic y equals sine x and y equals 2 sine x so that you can see the comparison. This 2 in front is our change, our vertical stretch. So our amplitude for our new graph is going to be a 2. Now, when we graph our sine curve, the sine of x, we said sine starts at 0. It goes up to a 1 at pi over 2. At pi, we're back to 0. At 3 pi over 2, we're at negative 1. And then back at 2 pi, we're back to 0. So this is my regular sine, basic sine curve. That is one period of it, from 0 to 2 pi. We are going to graph this one. It has a vertical stretch of 2. Now, when we stretch zeros, zeros don't move anywhere. But stretching a 1 turns it into a 2. And stretching a negative 1 turns it into a negative 2. So what happens is my graph gets stretched vertically so that it's taller. All right, our next example. We have a negative 3 in front. The negative is going to cause that reflection over the x-axis. The 3 is going to be our amplitude. So we have a vertical stretch of 3. Now we're going to start again with a basic cosine curve. Cosines start at 1, go to 0 at 90 degrees or pi over 2. We're at negative 1 for pi. 0 again for 3 pi over 2, or 270 degrees, and then at positive 1 again at 2 pi. So again, this is our basic cosine curve. And we said we are going to do two things. We're going to reflect it over the x-axis, and we are going to stretch it. So my 1, when I reflect it, turns into negative 1, and then stretching it means I'm timesing by 3, so I'm down here at negative 3. Stretching zeros don't do anything. Our negative 1 here is going to reflect to positive 1. It's going to get multiplied by 3 and be up here at 3. Again, zeros don't go anywhere. And our positive 1 is going to land down here at negative 3 again. So our graph has been reflected over the x-axis and stretched. The B term is another transformation. A normal cycle, or a one period for sine and cosine when there isn't any kind of horizontal stretch, is 0 to 2 pi. But this B value is going to cause a horizontal stretch or compression. So what that's going to do is it's going to change the period of my graph. The new period is going to be the normal 2 pi divided by whatever that B value is. All right, so this one says determine the amplitude and period for each equation and then graph two full periods. So our first one, we've got y equals the sine of 2x. My front number here, my A value is 1, so the amplitude would be just a 1. That means there's no vertical stretch, compression, or flip. But my B value is a 2, so the new period is going to be 2 pi divided by B, divided by 2. So my period here, one complete cycle will happen between 0 and 2 pi. Or sorry, between 0 and pi, instead of being between 0 and 2 pi. When we graph sine and cosine curves, we look at splitting it into 4 chunks, that period, because we have those 5 key points. We need 4 different intervals. So we are going to take this and look at what our increment will be. Our period here we said was pi. We want to divide it into 4 chunks. So each little increment is going to be pi over 4. So my first tick mark would be pi over 4, pi over 2, 3 pi over 4, and 1 pi. That's going to be 1 period. So from here to here is 1 period. Now they did say to graph 2 full periods, so we're going to have to go out another 4 increments, 1, 2, 3, 4. This would be another 1 pi, so we're at 2 pi now. That would be the second period. All right, we are graphing a sine curve. Sine curves start at 0. We said the amplitude is 1, so we aren't stretching or compressing at all. So my first high point will be here, then I'm back to 0, then I'm at my low point, back to 0. That is 1 period for sine. Notice that we've scrunched it horizontally, so it's a shorter period. Then I'm just going to repeat that. I went from 0 to a high point, back to 0, low point, back to 0. All right, so that's 2 periods of a sine curve. Our next example, we have 3 cosine 1/2 x. The 3 is going to affect the amplitude. All right, so we're going to stretch this vertically. It is a cosine curve, and our b value is 1/2. So our period is normally 2 pi. It's being divided by b. 2 pi divided by 1/2 gives us 4 pi. And then for our increments on our graph, we take the period and split it into 4 chunks. So each of my little tick marks will be pi. Now, that means we have stretched this out. Instead of going from 0 to 2 pi for 1 full period, we are going from 0 to 4 pi. So it is stretched horizontally. So I'm going to show that by using every other tick mark to show that we've stretched it out. We said our increments are going by pi. So this will be 1 pi, 2 pi, 3 pi, and 4 pi. That is 1 period from there to there. All right, it is a cosine curve. Cosines start high. We have an amplitude of 3, so instead of starting at 1, I'm going to start up here at 3. So I go from high to 0 to low. Now low in this case will be -3. Again, that vertical stretch. Back to 0, back to our high point. This will be 1 period for that cosine. Now they've asked me to graph 2 full periods. And since I'm out of graph paper on the right-hand side, I'm going to just continue on the left. So we're at -pi, -2 pi, -3 pi, -4 pi. Again, that would be 1 more period. Cosines start high, 0, low, 0, high. All right, so we've got 2 periods for cosine there. The other transformations that we've talked about would be shifting left or right, so horizontal shifts and vertical shifts. A horizontal shift is called a phase shift. Now, in our formula here, we've got bx minus c, but we really technically have to think of taking and factoring out that b term. So it's going to look like this. If we divide bx and c by b, we get x minus c divided by b. All right, so we've talked about changing the period, which will be the b piece, and then this will be our phase shift. Okay, so that's going to tell us how much we're shifting left or right. And it's the same for cosine. We can think of this as y equals a times the cosine of the quantity b times x minus c divided by b. Now, phase shifts can get a little tricky. Our normal period is 0 to 2 pi. Our new period can be found by taking that factor bx minus c and putting it between 0 and 2 pi and solving for x. That would give us our new starting and stopping point. For today, since we just have time to kind of do an introduction to these graphs, we're not going to go through a lot of detail on that, but keep in mind the basic shapes so that you can kind of tell if your graph has shifted left or right. The last transformation is our D piece. That is a vertical shift. So that would just take our graph and pick it up, move it up or down. If it's positive, it moves up. If it's negative, it moves down. Typically, our graphs oscillate around the x-axis. So we're here, all right? So we're going around, kind of bouncing back and forth around that x-axis. And for cosine, we start high, 0, low, 0, high. Again, we're oscillating around the x-axis. So what's going to happen if we do a vertical shift is we're going to have that line that we're oscillating around move up or down. All right, it says determine the amplitude, period, phase shift, and vertical shift, and then graph each of the following. So our first value, A, that is our new amplitude, so we've got a vertical stretch. Our B value here is a 2, that changes the period. For cosine, normal period is 2 pi. We are dividing it by our B terms, so what we've done is we've compressed horizontally. So instead of going from 0 to 2 pi for one period, we are only going from 0 to 1 pi. There is no phase shift, since there's no extra piece after our x here. This -1 at the end is a vertical shift. That's our D value. So we had an A, a B, and a D in this case. A D of -1 means we've shifted down 1. All right, so looking at a graph of this, it is a cosine curve. We're just going to graph one period for this. We said there's no phase shift, but one period is 1 pi. So we're going and cutting that, our increments. We're going to take that 1 pi and cut it into 4 chunks. So each increment would be pi over 4. So we've got pi over 4, pi over 2, 3 pi over 4, and 1 pi. That's going to get us one period. So normal would be starting for cosine high. We'd be here, then 0, then -1, 0, and 1. But we're doing several things to this. We are stretching it, so it's going up to 3's and -3's, and then we are also shifting everything down 1. So if we stretch everything, we'd be going here, here, -3, 0, +3. And now we're going to move everything down 1. So our final graph, our points would be here, everything moving down 1. So our graph would look like this. So we're kind of oscillating around that -1 line, y equals -1. All right. Our next one, we have a sine curve this time. Our A value is 1, so our amplitude is 1. There's no change there. Our B value is also 1, so a period has not changed. It's regular 0 to 2 pi. So the period has a length of 2 pi. Our increments will be 2 pi divided by 4, or pi over 2's. We do have a phase shift in this one. We are shifting, based on this, right 1 pi. And then we have a vertical shift. We are going to go up 2. All right, so let's look at what we can do on our graph. We said normal increments are pi over 2's. But we are shifting right pi. So we're not even going to start our period until here at pi. So I do need to make sure I have 4 tick marks, so I'm going to keep going. I've got 1 pi, 3 halves, 2 pi, 5 pi over 2, and 3 pi. So instead of going from 0 to 2 pi, I'm now shifting 1 pi to the right. I'm going to go from 1 pi to 3 pi. that will be my 1 period. Okay? Our amplitude is 1, so we don't have a stretch. We're going to shift it right 1 pi, and we're also going to shift up 2. It is a sine curve. Sines start at 0, so our normal graph would go from 0 up to 1, back to 0, down to -1, and back to 0. But we are going to shift that up 2. So we are going to be there, up 2, up 2, up 2, up 2, and up 2. All right, so continuing our sine curve, we have oscillated now around our line y equals 2. We've shifted everything up 2. All right. For example 5, it says determine the amplitude, period, phase shift, and vertical shift of each sine graph, and then write an equation. When you are taking your ACT or MCA tests, the most they would probably have you do is they would give you an equation or a graph and just ask you to interpret it. So that's kind of what they're asking in this example. It does say it is a sine curve, so we have to identify a typical sine curve, and that sine curve starts at 0 and goes up. So we're going to look at that much of it to determine what kind of things what transformations we've done. Notice that we are still oscillating about the x-axis. So we went up the same distance here that we went down here. So there was no vertical shift. So in our equation, our d value would be 0. But we did stretch it. So if you look at our values here, this would be a 2. So our amplitude is going to be a 2. We did not reflect it at all, so we're starting at 0 and going up instead of starting at 0 and going down, which would happen if we've reflected over the x-axis. So our amplitude is 2. It would be a positive a value of 2. Now, looking at the period, we are going from negative pi over 4 up to 3 pi over 4. That is a distance of 1 pi. So the period is just pi, but normal period for sine functions are 2 pi. So our period is always our 2 pi divided by b. And if we're getting a value of 1 pi, that means b must be 2 to make that compress down. And then we've also looked at a phase shift, because instead of starting here at 0, we've moved left pi over 4. So moving left pi over 4 means our c divided by b piece is going to be would be positive pi over 4. So let's look at our equation. Y equals a times the sine of b times x minus, c over b plus d. All right, we said our a value, our amplitude is 2. We said our b value was also a 2. And we've said we went left pi over 4, so we'd have a plus pi over 4 in there. And we said there is no d value. We didn't vertically shift it at all. Now, I could leave it like that, or I could distribute this 2. So another option, if this was a multiple choice question, would be the sine of 2x plus 2 times pi over 4 would be pi over 2. All right, our next example. Again, we have a sine curve. This time it is multiple choice, so they're giving me a few options. I'm going to look at a typical sine function. Now, there's a couple ways I could look at this. I could start here and go from there to there. That's a typical sine curve. But when I look at my options over here, none of these have any kind of horizontal shift. So that means we haven't shifted it at all. We have to be starting at 0. And so to get a sine curve here, I would have to move down and then back up. So that means I've reflected it over the x-axis. So my a value would have to be negative. So I could eliminate those two options. And then looking at my values here, they've marked this -6, so this would be they've marked it -5. This would be -3. So my A value is going to be -3, like I see in these two options. And then I have to determine which B value is correct. I am getting from 0 through 1 full cycle in the space of 1 pi. So the period is 1 pi, and period is always 2 pi divided by B. So to get that, again, B would have to be a 2. 2 pi divided by 2 will get us to 1 pi. So we are looking at this as our solution. All right, our third example. Again, it's a sine curve. We've been given a couple options here. No phase shift. So again, I'm looking from there through 1 full cycle to there. And if you look at your x-axis, they've got a 3 marked here. So this would be a 1, this would be a 2. Here we've got a 7, so each of our tick marks are going by 1s, which puts that at 5. So our amplitude should be a +5. We have not reflected it over the x-axis at all. And now I have to figure out my B term. We are getting 1 full period from here to here. So we're going from 0 to just a 2 instead of 2 pi. So if the period is 2, and our period is found by taking 2 pi divided by B, then B is going to have to be equivalent to pi to get those to drop out. So we need this solution. All right. So that is a very quick summary of sine-cosine graphs and their transformations. We're going to just look very quickly at some tangent curves, since that is a slightly different type of shape. We said our tangent function, our 1 period, goes from there to there. Now notice on this we've got some dotted lines. Those are vertical asymptotes. That is where tangent is undefined. And tangent is undefined at pi over 2, at 3 pi over 2, at negative pi over 2, negative 3 pi over 2, etc. The reason for that, think about your coordinates. At pi over 2, we are at 0, 1, and tangent is y divided by x. So if we take 1 divided by 0, we get an undefined value. So that's why we have those vertical asymptotes, those dotted lines. All of our transformations are going to be the same. A is our vertical stretch, compression, or reflection. The period, we talked earlier about it only being 1 pi wide, but it will still get divided by whatever our B, our horizontal stretch or compression is. We still have the same phase shift of C divided by B, and we still have the same vertical shift. So we aren't going to take time to graph these. We're just going to look at the types of transformations that have happened on them. So for our first one, we don't actually call it amplitude since there is no exact high and low point. Our graphs keep going up here and keep going down there. Okay, so there is no cutoff in terms of the amplitude like we had for sine and cosine. But we do have a vertical stretch. It's just not called amplitude. Okay, so we're going to stretch it, make it twice as tall. Our B value is 1, so period has not changed. It will still be just 1 pi. We do have a phase shift. We are shifting, since it's x minus pi over 2, we are shifting right pi over 2, and we are shifting up 4. That would be the type of transformation we'd have. For our next one, our A value is 1, so there's been no vertical stretch or compression or flip. Our B value is 1, so our period is still 1 pi. We have a phase shift there. We are shifting left 1 pi, and we are shifting everything down 1. All right. This one has a negative in front. That means we have reflected it over the x-axis. So instead of our curve coming like this, it's actually going to flip and look like that. All right. We have a b value here of 2. So period for this one is going to be pi divided by our b term. So we've had a horizontal compression. Now, we have shifted it left and right. We've got a phase shift in there. But remember, we have to factor that 2 out. So I want you to think of this as 2 times x minus, and if we take pi over 2 and divide out a 2, we have pi over 4. So we're actually shifting it right pi over 4. So all of your asymptotes would just shift pi over 4 units to the right, and then we could draw our curve in. Our last one, we have a vertical stretch by a factor of 4. We have a 2 in front, so just like our last example, our b value is 2. So the normal period, which is just 1 pi, gets divided by 2. Factoring that 2 out, I'm going to think of this as y equals 4 times the tangent of 2. Factoring it out, we've got x minus pi over 6. So we are shifting it right pi over 6, and we are shifting it up 5. All right, so again, on the ACT and MCA tests, the most trig graph type information they'd ask, given an equation, can you think of the transformations or identify the new period? Or given a graph, can you tell what the amplitude or equation might be? All right, for homework, you are going to work on a Delta math assignment that is listed in Schoology or in your agenda slide for you. And there is an extra credit tangent blue worksheet that you can do if you'd like.